Right, so in this video, I'm going to go over a few examples in the velocity and acceleration subtopic. A few of you have been struggling with this, so I just thought I'd go over it to help you secure those marks. Now, before I get into the examples, I do need to go over the equation you'll be using, um, in most of these examples at least. Now, the main equation is this: v squared equals u squared add 2as, and you do need to be able to derive that, or at least know where it comes from. So to start off, I'll just write down the equations we're going to manipulate to get this equation. The first one is knowing that the velocity is equal to distance over time. This in symbol form is v equals s. Yes, I know that's confusing. Over t. Now, just bear in mind that this velocity can sometimes be referred to as the average velocity. Obviously, if you're, say, running or walking or driving, your velocity isn't the same all the time. It does vary. So we can say that this is the average velocity over that distance. The other equation is knowing that an average velocity, if I gave you two velocities, the final one and the initial one, the average velocities the average velocity of that would just be adding those two velocities together and dividing by 2. So I'll say that v avg, or an average velocity, is equal to the initial velocity and the final velocity divided by 2. And the final equation I'm going to use is that acceleration is equal to the initial the final velocity minus the initial velocity over time. And we can use these three equations to get this equation that we want. Notice in this equation, there's no t, there's no time element. So I'm going to use this to try and get rid of the time element in the velocity and the acceleration equation. And to do that, I will first of all rearrange this to make t the subject. So I can say that t is equal to the distance or displacement over the velocity. So t is equal to s over v. We have a t in here, and I know that t is equal to this, so I can get rid of this t. So I will say, let's do it here. A is equal to v minus u over t. Then we can say that it's the same as saying v minus u over s and v there. Now remember, I said earlier on that this v here, because we've substituted this in, can be referred to as the average. So we can substitute this into here. Now that gives us v minus u over s multiplied by u add v over 2. Using the multiplication of your brackets, so you might use the FOIL method or the smiley face method. Whatever you use, you'll find out that it's equal to v squared minus u squared over 2s. We know that this is equal to a. Rearrange this and make v squared the subject. We get v squared is equal to u squared add 2as. So using these three equations, we've been able to get this equation. This is the equation you're expected to use in the following examples. Right, so this is the first example. It's made up of two sub-questions, each worth 2 marks, for a total of 4 marks. So the first question: a lorry travels 3,600 meters on a test track, accelerating constantly at 3 meters per second squared from standstill. What is its final velocity to 3 significant figures? Well, based off what we've just done, we're going to use the v squared equals u squared add 2as equation. You can kind of get a hint for this because it's asking for a final velocity. In other words, it wants you to have a final velocity or an initial velocity in your equation, and it hasn't given you a time. So you need an equation without the time element, and this equation satisfies all of that. So if we just start writing down what our parameters are right now, so we know that the initial velocity is 0 since it goes from standstill. We know the acceleration is 3 meters per second squared. And we know the distance, in this case, the displacement, or s, is equal to 3,600 meters. Plugging those into our equation, so v squared is equal to, well, this just goes to 0. 2 times 3 times 3,600. That gives us 21,600. And that's what v squared is equal to. We just want v. So we square root that. And that gives us 146.9 ... meters per second. It says it wants it in 3 significant figures, so we round that to 147 meters per second. And that's our final answer. The next example also wants us to use that equation. It's given us a final velocity, initial velocity, and an acceleration. So we're going to write down our equation once again. V squared equals u squared add 2as. This time we're trying to figure out what this is, what the displacement, what the distance s is. So let's just write down our parameters again. V is the final velocity. We know that's 30 meters per second. U is the initial velocity. We know that's 3 meters per second. And A is the acceleration. We are told that it's 5 meters per second squared. So if we start plugging those in, we get 30 squared is equal to 3 squared at 2 times 5 multiplied by s. Rearrange this just to make s on its own. So we get 30 squared minus 9 squared over 2 times 5. I'll just write that as 10 actually. Is equal to s. I don't know, I've written 9 squared. That should just be 9. So we get 30 squared. I'm just plugging this into my calculator. 30 squared minus 9 is 891 over 10. That's equal to s. And so we know that s, the distance, the displacement, is equal to 89.1 meters. Because that just comes out as 3 significant figures, we'll just leave it as it is. And so the final example is this. A ball is thrown vertically upwards and reaches a height of 28.8 meters. Ignoring air resistance and taking into account that the acceleration due to gravity is 10 meters per second squared, we need to find the initial upwards velocity and note that the ball comes to rest momentarily at the peak of its flight path. So if I just draw a short diagram to explain what's happening. So let's say this is the ground here. We're chucking a ball upwards and then it comes down, and this height is 28.8 meters. Up here, the ball is stationary momentarily. So we're also told that the acceleration due to gravity, so the acceleration downwards, is 10 meters per second squared. And so I'll just write 8 is equal to 10. Now, one thing you should do in situations like this, where there are different directions, is to appoint one direction as a positive direction. So anything moving in that direction is positive. In this case, it makes most sense to say that the downwards direction is positive since that's where the acceleration is acting. So I'll just write here that downwards means positive. If for some reason it was accelerating upwards at 10 meters per second squared, this would now be a negative 10 meters per second squared acceleration. Right. Moving on to the actual question, we only really care about this side. So I'm going to label that 1. And that's because we're only looking for the initial upwards velocity. So it going upwards, um, just as we've thrown it. So using v squared equals u squared plus 2as. I'm just going to write down my parameters again. So I already got a is equal to 10 meters per second squared. V we know is 0. This is the final velocity at the top. We're going to separate this into 2 different situations almost. So pretend this bit doesn't exist at all for now. So the final velocity is 0 at the top. U is what we're trying to figure out. And we already have A. And S is equal to 28.8 meters. So if we just plug that in, we know that this goes to 0. So you got 0 is equal to u squared plus 2 minus 10 times 28.8. Gone a bit weird there. And we'll just take this to the other side so that u is on its own. So we get that u squared is equal to, this ends up equaling minus 576. So when we take that to the other side, it becomes positive. So 576. And then we just need to square root that. So u is equal to square root of 576. And we get 24 meters per second. And that's your answer. So hopefully you found that this video helpful. And hopefully now you know what you need to do to get all the marks. It's a good idea to always write down the equation before you do your working out, and also to write down what the different parameters you're given are. And in scenarios like this, where you have 2 different directions, to appoint a direction as a positive direction.